Okay, so this tutorial is going to be, I think, quite different than Jorge's, but hopefully it'll be complementary too. And some of the notions that came up in Jorge's tutorial, I'll try to touch on. Largely, this is 30-plus slides of pictures that I stole from people in the audience. And this morning, I realized I didn't put their names next to any of the pictures, so I had to go back and try to remember who I stole the picture from. So if I got your name wrong, or if I attributed your work to someone else, I apologize. Basically, what I'm going to try to do here, there's going to be essentially no theory. It's just to try to touch on the notions. What Jorge talked about in the morning is this beautiful construction of an infinite dimensional mean field solution for glasses. And numerous times he asked the question, well, we don't know if this survives in low space dimensions. We don't know if this is relevant in 3 dimensions. So what I'm going to try to discuss or give you a flavor of is what is actually happening in real space, generally in low space dimensions, and then to try to ask the questions, how many of those things can we hope to be able to connect to our mean field solution, and how many of those things are probably hopeless? And that's going to set pretty much the final discussion, right? This is what we want to try to understand, why we're here in the room, and what, at least for some of the problems that we hope to address in the Simons collaboration, what are the challenges? So what I want to cover is, I'm going to start with a discussion of a phenomena called dynamical heterogeneity. And it says that I'm going to break this up into 2 parts, but really it's all qualitative. I mean, there's some minorly quantitative things, but I'm not going to talk about theoretical calculations of exponents, for example, or I might just allude to them. And then I want to talk about looking more closely at dynamical heterogeneity and break that down into trying to understand where that originates from in the actual real space structure of our liquid configurations, and how that propagates in those kinds of through those configurations. I will, throughout the entire presentation, try to connect what we're seeing on the screen or in pictures or in movies to theoretical concepts, many of them things that Jorge already discussed. If I have time, and I'm pretty sure I will, I'd like to also talk about things that are not directly related to supercooled liquids at finite temperature, which are the behavior of glasses at very, very low temperatures, like 1 Kelvin, and how that might be connected to these issues here. And also, very briefly, how some of the kinds of notions that I'll bring up that are pertinent for supercooled liquids are also relevant for that line that Jorge drew on the far left side of the board, which is the jamming line. Okay, so I think the fundamental question is, how do particles move as we supercool the liquid? Why is that motion interesting, and how is it different than what we expect from standard Brownian motion of particles in a typical liquid? So the picture that I took is from an experiment. And you can see these kinds of this kind of behavior if you just do simulations at relatively high temperatures, but you've gone below the onset of supercooling. And so basically, if you look at the probability for a single particle in your sample to displace a distance x in a time t, that's related to this function, which is called the Self-Van Hove function. And at low densities or at high temperatures, a large portion of that displacement probability distribution density is Gaussian. And what you start to see as you get closer and closer to the glass transition is that these fat, potentially exponential tails of the distribution get more and more palpable as the system gets closer to vitrification. So what this is saying is the probability of making a very large displacement is much more probable than you would expect from just your standard Brownian motion type picture. Now, it's always going to be true, even at relatively high temperatures, that if you go to far enough displacements, the central limit theorem doesn't work. So nothing says that there has to be a Gaussian distribution for arbitrarily large displacements. The point here is just that these fat tails are creeping closer and closer to x equals 0. This is also, by the way, a time-dependent thing. It depends on what time you're asking the question. Okay, and this kind of notion we'll come back to again. So this, I want you to keep in mind, is also single particle motion. Nothing says that this has to do with anything collective that's going on in the system. And this is actually one of the important things I think that gets lost in a subtle way often, is that lots of the things that we attribute under the collective umbrella of dynamical heterogeneity are perhaps facets of different aspects of physics. Some may be related to collective phenomena associated with growing length scales, and maybe some that are only remotely connected to those phenomena. And the question is how to make sense of all of these things together. Okay, so just to show you some pictures in a movie of actually now let's look at all the particles, not just the probability distribution function for a single particle. What you start to see is this same kind of collective phenomena that I was hinting at or alluding to. So this is from a simulation that Ludovic did. If you look at the displacement fields, you just basically map out how far particles have moved in some interval. What you see is in space, this is x and y here, that there's a propagation of this kind of large amplitude motion that on some time scale may actually extend over very, very large distances. I'm going to skip the middle thing and just show you a movie because I think that illustrates this maybe in the nicest sort of way. So the movie is from a microscopy experiment that was done by Eric Weeks 16 years ago in a paper in Science with Dave Waits, where they basically can image colloidal particles that are on the order of a micron in size. The goal is to try to density match this with the fluid so that gravity isn't ruining the experiment by forcing the system to be out of equilibrium and sedimenting. Oh, you can't do that perfectly, but on these timescales that's okay. They tried to remove the residual charge on these latex spheres. They can't really do that well. In fact, if you go back to this figure, you notice that these volume fractions are quite low. And presumably they're low, but you're still seeing this behavior because these things are charged. And so effectively they're interacting over longer length scales. It's like the spheres are effectively larger. But so we'll ignore all of those features. And the movie will play in the following way. When a particle undergoes a displacement that's larger than some threshold, we'll color it red. All the particles are the same. But when a jump occurs from a particle, let's say that's more than some small fraction of the actual particle diameter, we'll color it red. And if it doesn't, in that time interval, delta t, if it doesn't undergo such a motion, it stays as a little blue speck. Yes?
So just one transparency before. So you said that the big excursions are bigger than what you would expect in this was the tails. This, how do I have to understand it? As my particle is being swept by a wave that passed on top of it?
Let's defer the question, because I think the question of why this occurs is actually harder, deeper than just the phenomena. The phenomena is easy to look at, and we can see that it looks rather reproducible. It seems to be a quasi-universal feature of supercooled liquids. The question is, what is the underlying cause of this? And let's ask the question again at the end. I don't know if I have a good answer for you. Okay, so the movie's going to play where as time advances, this bar just goes up and then the movie loops. So it's going to loop over and over again. And then the percentage of the total number of imaged particles that are basically red or undergoing this larger scale displacement. So this is a sort of a binary thing. You're either blue or red. Red is you've made this displacement that's larger than some threshold value. And on the right side, the bar is telling you what percentage of the system is actually doing that at any given time interval. So, and if you can't read it, it goes from 0 to 8%. So, I mean, obviously what you see looks rather dramatic. You see this evidence of these, this jump-like motion that presumably was associated with those distributions that I showed you on the other slide. But you also see that the jumps aggregate spatially, so that there is some sort of avalanche-like behavior where particles move sort of together. There may be some collective aspect to this jumping motion that isn't just randomly pick a particle, make it jump further than you would guess by some sort of Brownian model. Basically, this occurs in regions of space that are correlated. So there's spatial correlation to this phenomena, which we'll call dynamic heterogeneity. At any given time, this is maybe only 5% of the system, yes?
Do you know if they have salt in the system?
They do have salt in the system. This is the way that they try to actually screen the charge. But I know for a fact, because I've looked at their trajectories, that, okay, I mean, there's no one in the room that did these experiments. And to give them credit, these are 16, 17 years old. There's a lot of junk in this. So I'm not quite sure they're really at equilibrium. I definitely know there's charge on the spheres, and I think the volume fraction here is something on the order of 40%, which if you took a real hard sphere system at 40% volume fraction, it's a Brownian system. So I want you to think of the system as effectively at a volume fraction of like 55%. I mean, they did some scaling of the volume fraction, but I don't know whether this was done right, and I do know that there's residual charge on the spheres. So you try to screen it with salt, but okay, so this is really interesting, and it sort of suggests that there is some sort of length scale associated with the dynamics. There's a collective, cooperative thing where if a particle moves, it needs its neighbors to move as well. And that's very interesting. And so the question that we'll keep coming back to is there a length scale associated with this phenomena, and does that length scale change as I get closer to the glass transition? You can ask lots of questions like this. What is the fractal dimension of these regions? Is that changing as a function of time? How does this depend on the time scale that I measure? How is this connected to the structure of the fluid? And many other questions. So the idea that the dynamics in a supercooled liquid could be or should be dynamically heterogeneous isn't a new thing. And it's not something that first appeared 15 years ago. If you think about very old models of liquids, and actually the Adam Gibbs model is one that is a precursor of the kinds of models that Jorge talked about. It's not the random first order theory, but it is sort of a motivator for the random first order theory. The notion was that there is this collective behavior that for particles to move, a bunch of particles together have to move. And that gets harder and harder because and therefore the length scale associated with that cooperative motion has to increase. This paper is 1965, so that's quite old. Before that, in trying to understand dielectric relaxation experiments, people like Glarum and other people postulated that there are sort of privileged defects in the system that could move around. And if you think about the notion of a privileged defect, and we'll come back to this again, then this is obviously, by construction, by hand, is a dynamically heterogeneous thing. Right? There are defects and non-defects. So this is an old story, and the question that's not addressed in a lot of the older theories is, although it is addressed in some of these questions are addressed in theories like Adam Gibbs, is how does this relate to the degree of supercooling? How does this depend on dimensionality? I'll come back to this because Jorge mentioned Patrick simulation, so I'll show you. I think this is actually very interesting, so I'll come back to this again. What are the consequences of dynamical heterogeneity? I'll show you one in terms of transport coefficients in a second. And also, in a sense, Jorge's question, what is the chicken and what is the egg? Why is this happening? Is this important? Or is this just sort of a sideshow for supercooling? And how do we quantify the motion? How do we quantify the length scales associated with the motion? What are the different length scales that are important in the problem? Okay, so one consequence that I think is very dramatic, which is mentioned often, is that this is an unfortunate consequence of switching to the Mac, because this was actually in the right place on mine. But either way, the Stokes-Einstein relation, which is basically if I try to measure the diffusion constant of my system, then there's a relationship between the viscosity, which is a bulk transport quantity, and the diffusion constant, which I can measure as a single particle quantity. And the relationship between that is very simple. Whether this is 6 or 4 or 5 or whatever depends on the boundary conditions. It's not important. The point that is important, however, is that as you supercool a liquid for many different kinds of glassy systems, this relationship is violated very strongly. Okay? And it's not surprising based on what I just showed you that it should be violated. So in principle, in a supercooled liquid, this might actually, in a system where the Stokes-Einstein relationship holds, alpha would be 0, right? And I'm just ignoring the KT for a second. But if alpha is larger than 0, then the difference between what you would expect in terms of the effective diffusion constant or the effective viscosity from the Stokes-Einstein relationship, as you get closer and closer to the glass transition, may be a few orders of magnitude different than what you actually measure. In particular, the diffusivity of the system may be 2 orders of magnitude larger at Tg or near Tg than you would expect from just measuring the viscosity and using the Stokes-Einstein relation. And that shouldn't necessarily be surprising. Basically, this decoupling between viscosity and diffusion is, in a sense, should be a consequence of the fact that the diffusion is going to be dominated by these rare particles that make large displacements. Right? And they're making displacements that are larger than you would expect, so the diffusion constant is effectively larger. The viscosity is dominated by the 95% of the particles that aren't really moving very much. Okay? And so these two things aren't necessarily coupled one-to-one in a simple relationship, and so you see a large, on a log scale, difference between what the actual effective Stokes-Einstein relationship is and what you would expect from Einstein's calculation. This just also shows you, and it's another way of showing you that if you measure the mean squared displacement, you get diffusive-like behavior, but underlying that is the particles that are contributing to it at different times in a sort of random way are making these very, very large jumps. You have to basically go beneath the averaging that gives you the standard mean squared displacement behavior to see that. Okay, so in a sense, the violation of the Stokes-Einstein relationship is a consequence of dynamic heterogeneity, and it's a very dramatic one. Not all glasses violate the Stokes-Einstein relation. So if I take SiO2 all the way down very close to the glass transition, the Stokes-Einstein relationship basically holds. So different systems will violate Stokes-Einstein to different degrees, and one of the things that I think is important to address is how is this behavior quantitatively connected to the other kinds of things that we'll talk about now. So are there any questions about, by the way, I should say people should just interrupt, and actually probably 30% of the stuff that I'm going to say is wrong. So you should correct me when I make a mistake. I put the slides together very quickly also, so if there are typos or whatever, tell me. And interrupt. It's much more fun if you interrupt if you have a question. Okay, so one of the things that probably struck you when you looked at that movie of colloidal particles is, in some sense, this might remind you of critical phenomena, but it's a critical phenomena that's in the dynamics of the particles. And so the question that was sort of talked around in several different ways in the morning is there a growing length scale or length scales that accompany the approach to the glass transition in supercooled liquids? And actually, there's a long history of looking for growing length scales. As Jorge said, you essentially can't have growing time scales without growing length scales. So we know that in glassy systems, as Jorge said, the viscosity, let's say, increases by 14 orders of magnitude when I go from room temperature in my system down to the glass transition temperature. So the time scales are growing massively over a relatively small temperature window. There has to be some growing time scale in the system, length scale in the system. Okay, and the question is, and maybe there's more than one growing length scale, and then we have to sort of determine in our minds what we think are the important growing length scales in the system. This isn't, of course, entirely true. I mean, I can come up with a model system like a Lorentz gas or something, and I just make the density larger and larger, but this is a fake. I mean, in a sense, there is a growing length scale in the system, but it's already put into the frozen particles. So I'm really talking about systems that all the components of the system can in principle ergodically sample the phase space, then this statement is basically a theorem. And so we want to understand what these growing length scales are. There's a really long history looking for this, and I think actually Sid did some simulations 30 years ago, sometime around 1990.
I'm not that old.
He's definitely that old. Where just looking in the structure as you supercool the system on the computer to try to find evidence of a growing length scale. This is what you would do, for example, let's say you take a liquid and you approach the critical point. You could just look at the structure factor of the liquid, right? And you would see evidence in the low Q behavior of a large upturn, so the compressibility is changing in a way that signals a diverging length scale, right? And you could fit that upturn to an Ornstein-Zernicke form or something and extract the length scale as you get to the critical point. But if you look at the structure of the liquid, as Jorge said, you don't see anything. And actually, I'll show you a simulation that puts on the same scale various different length scales, including the length scale that I just told you, which is sort of the equilibrium correlation length of the liquid, and that doesn't change at all. So this speaks to the fact that distilling a growing length scale in the system, even just let's say in the structure, is a very, very hard thing to do, and it's I think very puzzling for a long time. But as I said before, if you look at the dynamics, that is, if you look at the snapshot of a system at time t equals 0, so at the initial time, and then time t equals delta tau, the particle positions have moved. That's what that movie showed you, the Weeks and Weights movie showed you. And if you overlap these two configurations, then you can clearly delineate regions where, let's say, some collective motion has occurred. And so if we think about our favorite model of a critical point, the Ising model, and we think about static snapshots of the system, if we're very, very far from the critical point, we have domains of upspins and downspins where the effective length scale associated with those domains is very small. Right? As we move closer to the critical point, those domains take up the entire size of the system. And as we move further away from the critical point, the domains again become small. Okay? And if we wanted to quantify the fact that there's a diverging length scale associated with the transition from a paramagnet to a ferromagnet, we could define something like the magnetization of the system. Okay? And then we could, in various different ways use this to calculate susceptibilities, which would be like the fluctuations of the magnetization, and that this susceptibility should diverge at the critical point. Okay? Or we could directly measure the structure factor associated with the spins. And again, as I said, look at the low Q behavior of this quantity, and the divergence of this susceptibility is going to be associated with the divergence of the length scale that we extract directly from the static structure factor of the system that's associated with these growing domains of spins. So that's undergraduate textbook stat mech. I know that because I took undergraduate textbook stat mech from Sid, and he taught this. But this is not going to work, right? This is exactly what I said doesn't show you anything in a supercooled liquid. If you do this for the static configurations, and this is, let's say, the density of the liquid, then this is then just the static structure factor, the kind of thing you would measure in neutron scattering, and you see nothing as the system is being cooled down. But instead, if you generalize the concept of the magnetization to an order parameter that's dynamical, then you're going to be able to see this. So basically, the idea is the following. Let's say, just like in the movie that I showed, you freeze your confocal microscopy image or your simulation at time 0, and you note where all the particles are, and then you let the trajectory run to some time tau, and you look, and by eye it's not clear how much has changed, but if you take these two configurations and overlap them, then there's going to be clear regions where particles have moved, let's say in the upper right corner here. Okay? So what you can do is you can define an overlap, let's say, which is how far a particle has moved in an interval t. Okay, and look and consider that to be like the magnetization of the system, or M in the icing model, and look at the fluctuations of that quantity. Okay, and if you do that, what you actually see is you should then see this kind of growing length scale if it's actually growing. I mean, this is then an experimental tool in a sense to assess whether or not there are growing length scales associated with the dynamics in the system. So the thing that I want you to note, though, is this quantity, which I haven't listed on the slide, but I think is on the next slide. So I might define this to be something like the overlap is, let's say the particle I has moved some distance. Okay, and then I can sum over all the particles. Okay, it's a dynamical quantity that depends on two different times. Okay, so it's different than in the icing model. And we'll call this the dynamical overlap in the system. Okay, and we have to set what this length scale is. The answer is going to change depending on, just like in the Weeks and Weights movie, we have to set a threshold for when we say a particle has actually jumped or not, right? And that's going to change the answer. We also have to pick what time scale we care about. Okay, but then we could look at the fluctuations of this parameter Q, and presumably if there's something critical like in the dynamics, the susceptibility on some time scale and length scale associated with this parameter is going to grow and grow and grow like it did in the icing model, and I'm going to be able to extract a length scale from that by just generalizing what I did for the icing model to this overlap function. And as far as I know, the first attempt to do this was by Ramaswamy and Dasgupta. I think it's sometime in the early 90s. And they didn't see anything in their simulation, and they concluded that there's no growing length scale associated with the dynamics. They were actually doing the right thing as far as I can tell. I at one point did remember or know exactly what they did wrong. I think what they did wrong is they looked at too long a time scale. But Ludovic is shaking his head. So
I think they compute Q squared and Q over squared, and then do the subtraction.
no, I think they do. Well, we should look again. They did something, at least one thing wrong. Maybe several things. But they had a very good idea. It was the right thing to look for, and they didn't see anything. And as far as I know, then it was people like Giorgio and Silvio in the P-spin model to look at this quantity again a few years later. And as I'll discuss, but I'm not going to calculate or show, in the P-spin model, this type of susceptibility of the overlap is critical at the dynamical transition. So this is actually a prediction, in a sense, of the kinds of things you can get from a mean field model. This may seem surprising. You might think in a mean field system, how is it that I have a growing length scale? But of course, in the icing model and the Curie-Weiss model, you have a growing length scale. In fact, it grows too fast. So we'll come back to this in a second. Okay, so yeah, these are the formulas that, as I was concerned, don't come out when you transfer something from a PC to a Mac. But this is supposed to be like a step function overlap. This is a time-dependent thing, and then I put e to the iq dot r. And this is, let's say, a function that, depending on how I choose the threshold, is 0 or 1, and then I can measure both the fluctuations with respect to this quantity and the structure factor associated with it. So if you look, actually, there you can find very nice pictures in the literature for simulations. This is from Aaron Keyes and David Chandler in a large-scale simulation of a two-dimensional system. And depending on how you vary this parameter A, you can change the colors of this. If you make A really, really small or really, really large, you won't see anything. But if you choose A in the right way, then you'll see these very nice domains where there's some very large-scale motion and there's some residual motion that connects these kinds of things. And this is the sort of thing that I'll get to hopefully pretty soon. So this is a plot of this dynamical overlap at a given time. And if I look at the fluctuations of this, I'm going to be able to measure a susceptibility. And from that, I can also extract a length scale. And this would be a dynamical length scale. It may have nothing necessarily to do with thermodynamics in the system, or it may have to do with thermodynamics in the system in a trivial way. And this is one of the things that I want to discuss as we go on. So if you do these calculations that I just mentioned, this is what what this chi-4 susceptibility looks like. This is for Leonard-Jones simulations. The onset of supercooling is something like T = 1. So at very, very high temperature, there's just a very, very small bump here. And what you see is at a time scale that's more or less the alpha relaxation time of the system, which I didn't define for you. If you go back and look at this quantity, the overlap, and you take the thermal average of this, it's sort of like the intermediate scattering function that you measure in neutron scattering. And if you look at the time scale of the decay of that function, the 1/e time of that you can crudely call the relaxation time of the system. So I'll call that the alpha relaxation time of the system. Okay, so the peak of this guy is somewhere close to the alpha relaxation time of the system, so you see that it's moving to the right and going to longer and longer times. This is on a log scale. And the height associated with the susceptibility is growing as supercooling progresses. And this isn't even a very low temperature. You see it's very, very sensitive to lowering the temperature. So basically, this signals the idea that there is a growing length scale in the system. If you then try to extract that length scale by generalizing to the structure factor of the overlap, you can do your best to try to fit this to something like an Ornstein-Zernicke behavior. And what you generally find is that there is a length scale that's growing. And depending on what system you want to simulate or what system you're looking at, the length scale grows, let's say, from 1 particle diameter to something like 4 or 5 particle diameters as you get to the temperatures where simulations become hard to do. Okay, so I don't know whether you think 5 particle diameters is a large length scale or a small length scale. Okay, it's not relative to anything. So if this were critical phenomena and you wanted to think about the temperature where you stop your simulation as something close to the critical temperature, then that would be a small length scale. But actually, if you continue to extrapolate this behavior to the glass transition, it's quite a large length scale, something like 30 particle diameters. And in some sense, that's either satisfying or very troubling, depending on your perspective on theory. And no one says that this behavior has to continue, by the way. Maybe it levels off or it goes down. So this is something I want to keep in mind and come back to. But basically, what you find from these kinds of nonlinear dynamical susceptibilities is that there is a growing length scale. Once you start going to temperatures where you start to see non-exponential relaxation in the system and non-Arrhenius behavior in the transport coefficients, right at that temperature, you start to see this length scale grow from something that's on the order of the particle size to something that's on the order of a handful of particles, let's say 5 particles, near where fits of this dynamical transition that Jorge talked about you would get by extrapolation in your simulation. There's a lot, I'm glossing over a lot of things. So there's a lot, there had been and there is a lot of debate about the best way to extract this length scale. And there's lots of other subtleties. I'll only mention a few of them. One of them actually is that even though the length scale itself is not very large, if you want to do extrapolations like this, you have to go to ridiculously large systems to get accurate extrapolations. So if you go to 30,000 particles, you find length scales that are about half as large as if you went to 100,000 particles. Ludwig simulations here are 1,000 particles. So he got lucky, right? If you do 1,000 particles and you do this very crude fitting, you get about the right answer that you get from 100,000 particles, where you really have a very large box. So this is kind of a mess. And there are probably better ways to do this. But that is what it is. I'm not going to, yes?
May I make a comment?
Mm-hmm.
I mean, one of the things that I do not like is to look to the correlation function in momentum space.
Mm-hmm.
I mean, to start the correlation length.
Yeah.
I think that what should be done.
Yeah, I think on the next slide, well, here I talk about,
okay.
yeah, I'll get there, yeah.
Okay, fine.
I don't disagree. I'm just going through historically what people do. In some sense, you could ask whether you get a better, just from the standpoint of numerics, not from understanding physics, whether you get a better calculation of the correlation length in real space.
Look, the part is the following. People doing high energy physics are very interesting to have a measurement high precision measurement of the correlation lengths because the correlation lengths correspond to the mass of the particle. So when you do QCT experiment, you have to put the correlation length of the proton, give the proton mass, the correlation length of the pi, give the pi mass, and so on. All analysis is done in configuration space, and never seen any paper whatsoever.
Yeah, I mean, one of the difficulties here, and it's maybe different in high energy physics, is that on intermediate length scales, there's a lot of oscillation in real space as well, or there's some behavior in real space that's not clearly asymptotic.
Ryan, that is surprising that both communities want to measure correlation lengths. One community always come into space, and another community.
But I think, so some people in the room have measured this also in configuration space. We'll come back to it. I mean, I'm not disagreeing at all. So in principle, if one did everything right, you should get the same answer. What I'm trying to point out is if you do it in momentum space, it's tricky. It's not clear to me that it's that much less tricky in configuration space, but we can discuss it. I think it's tricky in general. Okay, so one thing that I wanted to point out is that you can measure these kinds of nonlinear susceptibilities associated with growing dynamical length scales in lots of different systems. So you can take bacterial colonies and measure these kinds of things. This is, in driven granular systems, you see very, very similar things, even though this is not driven by temperature. This is driven by shaking the configuration itself. This picture doesn't come out very well, but in real space, if you look at the overlap, you can see these growing domains, and you can translate that into growing susceptibilities and length scales. The exponents may change, but the behavior has some sort of flavor of being reproducible from different systems. Yes?
So on the last slide, you mentioned that you're looking at a length scale that's something like 5 particle lengths, but that you need to simulate a system 100,000 particles to see that length scale.
It's not that you need 100,000 particles to see the length scale, but part of it is that it's not really clear what the right scaling form is that you should. Goes back to Giorgio's point, I think. What the right scaling form is that you want to fit your data to. So if you do 1,000 particle simulations, you're limited to some value of wave vector that's the lowest wave vector you can go to. That below that doesn't mean anything because of the periodic boundary conditions of the system. So it's not that you can't see the length scale. It's not that there are finite size effects that are so strong, although in some systems people claim they are. Let's say in these systems, the length scales really are small-ish. Certainly, you don't see large finite size effects in the dynamics when you're already at 1,000 particles. But in order to do an extrapolation here, you'll get different answers depending on what scaling form you use. So whether I take this to be purely Ornstein-Zernicke or I make it 1 plus length scale times q to a power that's not 2, will change the answer. So in order to do this in a way that's really good, you want to have a way that's just basically taking the lowest 2 k points and subtracting them and getting the length from that. And for that, you need to have a large box to do it. So I know it seems weird that you would need a very, very large system to do an extrapolation to get something that's associated with the length scale that's 5 particles. But this is the way it is.
Okay. Can you just recall quickly what was the definition of susceptibility?
Yeah, so I take an overlap and I basically take the fluctuations of the overlap. So I take, yeah, so basically overlap is already time dependent. So it is measured as the displacement in some time interval. And the result is going to depend on the time interval. So as you see here, there's a peak in this, but if I let time get very, very large, everything is decorrelated. The whole system is relaxed, and it's as if it's not critical at all. So the criticality is really in the dynamics, and you have to look at the right length scale and time scale to see anything.
The variance is at least also, it shows up in space, right? It's the same as
Yeah, right. Right, but if I'm as I'll show you in a second, the susceptibility is the spatially integrated real space version of what Giorgio was saying. So, yes?
Are you going to show us experiments with liquids?
I don't know. Do you consider this a liquid or? I guess not, but
No, because what I always found worrying is that it seems to me that this very length on the liquid is much shorter than in these disk systems.
you're talking about the A parameter. This is also true in the colloids, as far as I can gather, which are liquids, right? I mean, it's not orthoterphenyl or glycerol, but there, of course, you know. So I'm actually not going to show any direct. I mean, you can try to look to extract these kinds of things from dielectric relaxation, but they're not exactly these functions. And you can use something that I'll talk about in a second to estimate an upper bound for these, but they're not direct measurements of, if you're talking about molecular liquids. Okay, so as we were discussing, if you wanted to do this in real space, which I think is a perfectly good thing to do, then you can just work in real space directly or take the Fourier transform of the thing that I defined in Q space to get a nonlinear real space Van Hove-like function. And if the form that I wrote out before in Q space is right, then this is basically the form in R space. And if I integrate this over all space, that should be chi4. Okay, so the chi4 is going to be growing like the length scale to some power. Let's say 3 or 2, something like that. Okay, so the growth that I showed you here before is going to be something like the length that is extracted here raised to some small power. Okay, these are just some comments. From computer simulation, you could ask whether the length scale is changing as a function of time. I showed you that the susceptibility grows from some small valued peaks and then it decays. There is some evidence from computer simulation that if I look at relatively short times, which we normally just associate with the vibrations of the system, that there is a growing, the same growing length scale that governs the behavior at the alpha relaxation time is governing the growth of the susceptibility at this time scale, which is a very short time. So basically, the vibrations in the system that are associated with the modes in the system aren't just stupid, uncorrelated vibrations. They're correlated in some way that's reflecting the correlation of the relaxation of the liquid on longer time scales, which is interesting and important. And that's actually a prediction of mean field theory. That's a prediction of the dynamical version at high temperatures of the theory that Jorge talked about in the morning. It's also a prediction of that theory that the shape or the exponents associated with the relaxation are different in the beta and alpha regime. And this is also, there's evidence from computer simulation that this is true. So this is sort of indirect, and it's not confirmation that the exponents that mean field theory predicts are correct, but qualitatively, these two things are something that is in harmony with the mean field perspective, even though the system is in 3 dimensions. And so those two things are that the length scale associated with the alpha relaxation time that I've extracted from my computer simulation, either in real time or in Q space, is this very same length scale that's growing even when it looks like the system is just vibrating. Okay, and that but the shape associated with the fluctuations and the growing dynamical length scale may change. It may be more fractal-like or diffuse at short times and then more compact at longer times. Okay. So I'm not going to really talk about this, but maybe we'll come back to some of the issues there. So what are the predictions of mean field theory with respect to these kinds of growing length scales? Basically, mode coupling theory, which is the high temperature, more or less the high temperature theory associated with random first order theory, although not, as Jorge said, not exactly, predicts a relationship between the growing relaxation times in the system and the growing length scales in the system that is of the standard dynamical critical phenomena form. So it's a power law. And the power law that the mean field theory predicts, however, is very large. So the length scales grow very slowly. The actual power law that you can fit over some restricted range is something like 4, let's say. In the mean field theory, it's something like 9. So it's quantitatively wrong, but qualitatively right. However, if you take the same data and fit it over a wider temperature range, you find that this power law maybe isn't great. Maybe you would fit it better to some sort of activated-like form. And this may seem natural to you based on nucleation type arguments or anything else, but actually this is not natural to me. In particular because this is not really the length scale that should be in this formula. Right? It should not be the length scale at high temperature that follows this space-time scaling law, at least as far as I believe. So this is very subtle and I don't understand it, and maybe we can discuss it. But this is empirically the case. Jorge, did you have a question? Okay. Now, one thing that I'm not going to discuss because it's tedious and it's confusing, but it's actually very helpful also, is that if you want to actually calculate these quantities and extract these length scales, it actually matters what thermodynamic ensemble you use. And this is actually physical. It may seem unphysical, but it actually makes sense. I'm not going to talk about it, but what this does is it leads to a bound that is useful because basically the fluctuations from one ensemble to another can be written in a piecewise form where one of the terms is basically related to very, very simple information like 2-point correlation functions and the derivatives of those correlation functions or those relaxation times. And you can show then if you just take that piece, that actually is an upper bound on the susceptibility itself. And this is what I was mentioning in reference to Jorge's question on liquid. So if you take glycerol or something, you can get an upper bound on what the susceptibility should be near the glass transition from this. And the interesting thing is when you use that bound, it should more or less give you, if the bound is saturated, it should give you an accurate estimate of the length scale. And what you find are actually quite small length scales, even at TG, which is far below what we can do in the computer. So the question is, how is it possible that my length scale is 5 particle diameters at the dynamical transition, but it's still seemingly either that size or smaller at TG in the experiment? Okay, and what is the relationship, let's say, to things that I talked about before, like Stokes-Einstein breakdown and so on? These are very interesting questions, and I'll briefly come back to this again. Okay, so so are there any questions about this? This is sort of one way to measure a length scale in the system. It's not necessarily the most important length scale, and it's not the only length scale. So if we go back to the kind of theory that Jorge talked about in the morning, let's say we take the p-spin model, there are actually 2 important length scales, one of them being a thermodynamic length scale and one of them being this dynamical length scale. And they grow differently in the temperature regime that's associated with computer simulations. So this is also, in a sense, an important prediction of mean field theories, that the length scale that I'll define for you later associated with static structure should change maybe in a slower or different way than the one associated with the dynamics. So we'll come back to this. So, but right now I want to put away the notion of quantifying length scales, and I just want to ask, overall, for the phenomena that I'm discussing, the dynamical heterogeneity in the system, is there a way that we can understand what in the structure is encoding this kind of behavior? Are there locally preferred structures that give rise to regions that are harder or softer in the system? Are there other structural motifs? Free volume being a traditional one that goes back 50 years. Maybe there are other kinds of ways to define these kinds of structural length scales. And so what is, obviously it's natural to think that there's something in the structure that's encoding this dynamical heterogeneity. Is there a way we can uncover what it is? And how can we best predict where motion will occur in a system if I could just look at the snapshot of the system? Okay, so this is a natural question. And one very nice, trivially obvious, but something that hadn't been written down, I think, until 10 years ago, tool to uncover these kinds of structural motifs is something called the isoconfigurational ensemble and propensity. So this is very, very simple. Let me just explain what it is. Let's say I have a computer simulation of a liquid. In this case, it's a 2-dimensional binary liquid. And I want to know, is there something in the structure that encodes the dynamic heterogeneity that we've been talking about? So what I can do is I can make an ensemble where I start with the very, very same configuration. So when you do a computer simulation, or when someone in the room does it, when Patrick does a computer simulation, and he wants to calculate a correlation function, he averages over lots of different initial conditions. right? Then you get better averaging and you get a better answer. But the whole point of the ISO configurational ensembles don't average over different initial conditions. Break the problem up into the initial condition being fixed. So all the particles are prescribed exactly where they are. Just sample randomly different velocities associated with the temperature at which you equilibrated the system. And run trajectories, each with a different Maxwell-Boltzmann distribution of velocities, then just look what happens. Okay? If structure didn't say anything about dynamics, what you would see in one configuration is some things would move over here, and in another one they'd move over here. And when you went to the limit of having lots of different runs associated with the different sampling of velocities, you would basically get that on average each particle has moved the same amount no matter where it was in the configuration. But that's not what you see. What you actually see is that there are regions of your configuration in your ISO configurational member of your ISO configurational ensemble that are more likely or have a higher propensity for motion on some time scale than other ones. So here would be, let's say, 3 different members of trajectories that started from the same initial configuration. And if you did many of these and you put a circle around the particle associated with the size of the displacement that the particle undergoes in some time scale delta t, then a large circle being a large displacement and a small dot being a small displacement, you find that there are regions of higher propensity than other regions. Okay, so there's, clearly something in the structure, let's say soft spots or soft modes as we'll see or something, which effectively encodes behavior that's related to the difference in motion between one particle and another in the system. Okay, so one thing that I actually want to point out, and this was written down in a nice paper by Rob Jack and Ludovic, is that just because you have something that you call propensity doesn't mean that you can make predictions from it. Even if I calculate the map of the propensity, it doesn't mean that I could say in a given run this particle is going to move, right? That doesn't make much sense. And in fact, you can really see that clearly if you look at the overlap between just the regular displacement distribution and the propensity distribution. There's a strong overlap. So on a given single particle length scale, you cannot say whether a particle is going to move in a given run. But what's actually interesting, and this sort of connects to the growing dynamical length scale business that we talked about before, is if I take regions and I just average over a small local environment, then actually that does become more and more predictive. That if I actually say, what is the probability that I have motion in this region instead of that this particular particle moves, then you actually do see a decoupling between those things. So if I just average over 2 particle diameters and I calculate, and I'm not going to write down the formulas, but I calculate the right way to average over the ISO configurational ensemble, I see that there's a higher and higher predictability, something like 40%, let's say, at the longest time scales in the system when I average over a ball. But if I just look at the single particle level, that's always something that stays very small on the alpha relaxation time. So this is, again, something interesting that basically says if you connect the 2 kinds of themes we've talked about before, the ISO configurational ensemble being a way to distinguish particle motion, but that I have to do this on a scale that's associated with some collective behavior, then you can actually make some predictions based on this.
Can you extract a length scale from this propensity?
You can, and it's actually in Ludovic and Rob's paper. The thing that is funny about it is it grows more slowly, this is what I remember, than grows more slowly than the chi-4 length scale does. It actually grows much more like the mean field theory predicts. And I don't know if that's a coincidence or not, because
You have to compare 2 numbers that are different.
Right, but you can basically what you can do is you can take propensity maps of the overlap, dynamical overlap, and look at the fluctuations of those and look. I think actually in that paper Ludovic did look in both real space and Q space, right? Is that right? Or at least in the calculations that eventually led to the paper. I don't know if they all appeared in the paper. But the ones in the paper are Q-space ones. Yes?
Also in field theory predicts that this grows slower than the...
Okay, yeah, that's right. So, but the other interesting thing, which I think is a coincidence, is that the slowness of the growth in the one calculated case by Ludovic is actually very, very much like the growth that you would predict in the liquid, not in the propensity, which I think is a coincidence. But yes, you have a paper from 10 years ago or something where you actually do these kinds of propensity-like calculations. So that.
Oh, didn't Aaron Geeks also try to, don't those papers also try to calculate a length from a configuration thing, but they were basically trying to show that the length scale was single particle size no matter what.
I don't think so.
No, in Fitzgerald.
No, I think in their paper, the length scale that they compute in that paper is something different, which I'll come back to. Okay, so very briefly, one can then ask, okay, I have a way to assess in real space where things are likely to move. Why is this particular region have a higher propensity than any other region? And you can try to do ways of assessing correlation between your favorite metric. And I'm not going to belabor it. In some systems, if you look at standard statistical measures like Spearman coefficient or precision, these are certain kinds of Leonard-Jones-like systems. The correlation between some sort of icosahedral order and whether or not particles are slow or fast or highly propensed or have a low propensity is actually quite good. So if I ask, for instance, in this particular model, I look for the regions, let's say coarse-grained over a few particles, where I have the highest density of interpenetrating clusters of a particular icosahedral order. What is the likelihood that that region is a slow region? You find there's a very strong correlation. Okay? In other systems, there's almost no correlation with these measures, but maybe there's some other structural feature that this correlates with. And actually there's some, Andrea's not here, but there's some nice ideas to use machine learning and have the computer tell you what that metric is. And I think that there's early stages for this, but I think it looks very promising as a way to sort of, if you really care at the level of very high predictability, maybe there's ways to train the computer to tell you what that structural feature is. All right, so let's see. So another thing that's been popular and is interesting and connects actually with jamming is the notion that maybe regions that are of high propensity or low propensity are associated with the soft mode structure of the system. So just to go into this very briefly, what you can do is take your system on the computer and you can calculate the Hessian matrix as if the system is one gigantic molecule, right? So it's got a 3n by 3n Hessian matrix. You diagonalize it, and you basically classify all of the polarizations associated with the normal modes you find from the Hessian matrix. And you look at them in real space, right? So you can look at the polarization of modes. So you'll find lots of different interesting features, and it would take 2 hours to just have a talk about soft modes, but some of these modes will just look like plane waves, right? So you'll see some intermixing between plane wave-like behavior. Some of these modes will be very, very localized, so the polarization would just be a few particles. And some of them are some hybridization of a plane wave and some very, very localized feature. And those are generally what we call the soft modes of the system. They basically extend over some length scale, and they do have a length scale associated with them, but they're neither plane wave nor totally localized. Okay? There's some hybrid of a plane wave and a localized mode. And actually, if you look at propensity maps in the system, in some systems, this is probably not true in all, and it's worth going back and looking at this. If you look in real space in the low frequency band at the soft mode structure, you find a relatively interesting and high degree of correlation between regions that have high propensity and regions where the polarization is largest in the soft modes. Okay, and in fact, you can try to use that to reconstruct, if I just sum as a random superposition over the 50 lowest frequency soft modes, I can create a map associated with that, and then if I put the particles that move the most in my propensity map, the correlations are not terrible. Of course, this system is a bad one, I think, to do these kinds of calculations on, because there's a lot of crystalline order in these two-dimensional bidisperse soft sphere systems. In other systems, this correlation may be better or worse. One of the things, well, there's lots of interesting things here, and as I'll show you very briefly, there are connections with what you would expect in systems that are near the jamming threshold associated with soft mode. So the thing that's interesting here is one of the primary tools for understanding, let's say, the length scales that might diverge at the jamming threshold are actually looking at, let's say, the structure factor associated with the transverse component of these mode structures. And near the jamming transition, because of the isostatic nature of the particle configurations, these length scales may diverge or will diverge. Here, we don't see anything like that, but what's quite interesting is the particle motion can be decomposed in a way where there's a correlation between the soft mode structure and where particles move. The other thing is that this also connects in some vague way to the mean field picture, even though this is a real space thing and there's some structural spatial correlation, which is that in some sense you can think about notions associated, let's say, with the mode coupling threshold or the dynamical threshold as one associated with the behavior of the soft modes. And I'm not going to go into this, but I think Jorge alluded to this very cryptically this morning. So I think this is also very interesting. Okay, so yes.
About the correlation with the mode and the propensity and everything, has it been done on into dimensions on the air?
No, so in the paper that I showed you, we did it also in 3D, but we did it in the same crappy system in 3D. The correlations are slightly lower, but they're sizable. But to me also the question isn't just 2D or 3D. I think, by the way, Ludovic's probably asking because there's more and more evidence that 2D and 3D are very different. And that 2D liquids, many of which are great to show, and I've showed lots of pictures because it's very easy to represent things in 2D, that the behavior of the system in terms of length scales, elasticity, and finite size effects are dramatically different in 2 dimensions than 3 dimensions. I think this is actually a very interesting question that I'm going to pose at the end when we talk about what would be nice to look at. So there isn't a whole lot, I think, done in 3D, but there is work done in 3D. I mean, in particular in that paper, but I think there's other work in 3D, but it's not, I don't think it's very systematic. And the other question is, how does it depend on the system that you look at? Maybe some people from Andrea's group have looked at this in association with the machine learning stuff as well, but I don't know.
In Rob's paper on PRL from last year with the metric for calculating correlation, doesn't he look at normal modes and compare with propensity? I think so. But it's not in such a real space way.
Okay, so now we've talked about growing dynamical length scales. We've talked about the notion that there's a lot of interesting physics to be looked at if you ask questions like what are the structural motifs that give rise to the kind of dynamic heterogeneity that I've showed you pictures and movies of. You can also ask whether or not there are growing structural length scales. Of course, one question to ask is there a growing structural length scale associated with the soft modes? And I'll show you that there definitely is one close to jamming. And I'll show you a picture from one of Sid's papers. I think Ludovic and I looked for this 10 years ago in the soft mode structure, and it's not clear that anything is really happening, at least the way the pictures were made in the plot on the previous slide. So I think this is an interesting question. But what I want to start to address now is the possibility that there is a more systematic and maybe order agnostic way to assess growing static length scales. And actually the length scale that I'm going to talk about in some sense is the fundamental length scale that is associated with the theory that Jorge talked about in the morning. So the idea is the following, and I think the idea goes back before this paper, but I think this paper by Giulio and Jean-Philippe was very nice, at least in giving the picture for it, which is, let's say I have a computer simulation. I have, this picture is actually very nicely generated by Glenn, who's sitting there, some binary system of spheres, and I imagine that I create, I draw a sphere of radius r at the center of my configuration, and then I choose to freeze all of the particles that are outside this ball, okay, and then I try to sample all the different configurations inside the ball. Okay, so obviously if the sphere is, if the ball that I draw is one particle wide, there's only one configuration inside, right? It's just that there's the particle on the sphere that I drew. okay? And what I can do is I can ask in a thermodynamic sense, what is the overlap thermodynamically between all of the different configurations inside that sphere that I've sampled. And I have to make sure that I'm not asking a dynamical question. I want to ask a thermodynamic question. So I basically want to ask the conditional probability to have all the particles outside the ball in their same positions, but all the possible different ways I can arrange the particles inside the ball, and that's clearly going to be a function of the size of the ball that I draw. So if the ball is literally one particle wide, there's one configuration, the overlap is unity. And then if I make this sphere bigger and bigger and bigger, then the boundary effect from the frozen particles on the outside of the ball will have less and less influence in setting what the actual configurations inside the ball can be, and the overlap will go to 0. And there should be some length scale associated with that. And if there's a growing length scale in the system, then I should be able to see it by taking configurations at lower and lower temperatures and doing the same experiment, just growing the size of the sphere that separates the frozen particles from the one that I want to ergodically sample, and looking at how the decay of the correlations associated with all the properly sampled configurations inside the ball change as a function of the temperature or the density of the system. Okay? Because I am correlating, let's say, points at the center of the ball with the entire set of configurations on the outside of the ball, this is commonly called the point-to-set correlations. And this is, in a sense, the fundamental length scale associated with the kinds of things that are growing in the random first order theory. Actually, both of the length scales that we're talking about, the point-to-set length and also the chi-4 length, grow differently in that theory. But in a sense, this is the length scale that Jorge was talking about should diverge at some ideal glass transition temperature. Okay? So this is from some early computer experiments showing low temperature to high temp, the other way around, high temperature to low temperature. Obviously, it looks superficially like this length scale is growing. This is from some very recent work of Patrick and Sho's, which I think is really nice, where I think they did the best job of extracting these kinds of correlations. And what you see is the chi-4 length scale is growing. It's something like, in this case, something like 2 to 3 particles, when it's normalized against what it is at this temperature. Maybe it's 4 or 5 when it's normalized at t equals 1. The point-to-set length scale associated with the decay of correlations thermodynamically is growing. The absolute length scales are smaller, and it's not labeled properly here, but this is the static correlation length of the liquid. So it's basically not growing at all. So what we find is that the other interesting thing that I want to point out about this length scale is that I've made no assumption about what it is in the structure that's encoding the growth of this length scale. So in that sense, doesn't depend on any structural motif. It doesn't depend on whether I'm talking about icosahedra or anything else. All I have to do is do this experiment. Maybe it's time consuming on the computer. It does get very, very hard to sample the configurations for small cavities, and you have to do the sampling well. But if you do this carefully, and there are checks to see that you've done it carefully, then you can extract this length scale, and it is growing, but it's growing, at least in the regime associated with the computer simulations we can do. It's growing in a way that's different than the dynamical length scale, and this is again a prediction of the mean field theory.
When I look at that one, it seems that it goes up to, I don't know, 4 maybe.
Yeah.
And when I look at the purple one, it's less.
Yes.
So why is this? Is there a simple explanation?
Why the dynamical length scale is growing differently than the point-to-set one?
No, this is older than this one, but
The results grow significantly faster.
Yeah. Yeah, are you asking why is this so pathetically small?
as compared to that one, or why is that so?
Oh, this between these two.
Yeah.
It's a different system.
It is a different system. I think if we could be honest, I think they did sample their things correctly. They use a swapping technique that for that system works. I think what may be happening, this is just a speculation, is that there is some crystalline order even in the cavity that is something you would want to remove that makes it look like the length scale is growing larger than than it should be. But this is just a guess. I don't know. I mean, we reproduce the results, and I think the results are right. And the other thing that's quite interesting is I don't think even their temperatures are effectively lower than Cho's and Patrick's. They're really actually effectively higher, and still the length is growing by a factor of 3.5, something like that.
I think it also depends on how you fit it, which is why in their paper they have a sort of fitting dependent way of calculating the length, right? So in the older thing, they fit it to compress exponential of e minus r over big R to some power. And when we did our paper, which isn't up here in between, we did r minus a over r, and you get a different result because it doesn't go to 1 at r equals 0, right? It really should go to 1 at r equals 1, or something like that.
The funny thing is, I think if we fit it the way they fit it, we get Cho's result. So I don't know for this system. I mean, Glenn's point is right that the way that they do the extraction of the length is better, and whether or not this length is really growing the way they say may be also a artifact of the fitting procedure, hearkening back to what we were saying about the dynamic length. I mean, the point I think is interesting is that the length is growing, and it's growing modestly, but in my mind it's not clear that this is too slow in any theoretical sense. I mean, it's certainly not like what you have in the static correlation length of the two-point function. Okay, just one other quick thing, because I...
There is one numerical experiment that was done by Procaccia 1 year and a half, I guess, in which was able to using swapping technique to go to low temperature and see a much bigger increase of the correlation.
Yeah, maybe I don't know what I think about that. I think it's interesting. I mean, first of all, his system is different than these. It's a trinary system.
Yes, with 10%.
Right. I can't remember in that paper whether he's calculating this using the sort of the crossover length scale and the modes, or he's actually doing the point to set.
Doing the computation of the correlation lengths looking to the loss eigenvalue.
Right, exactly.
But I mean, I think the
Right.
main point is that for this type of system, the swapping, things is you can determinize to temperatures which are 25%
Right.
below, and the region of increase of the correlation length, serious increase of the correlation length.
No, I
Just
agree.
The region
Yeah.
that can be touched only by this determination.
I think that's true, and I think that's fine. And to me, actually, this growth is fine also.
So it would be nice maybe if one could do to show people they had the stuff with the new system, with new implementation, and see what happens.
I agree. Actually, I think a lot of the things that I would propose are interesting to do based on the things I'm talking about would benefit from carefully choosing systems where swapping is efficient and using those. This may be true, but I also do think that Ludovic himself is using swapping for certain systems that hopefully aren't phase separating. So I think the question still stands. I mean, I think it would be useful to do this. Okay, one other thing is that one could go back to this, this question of real space propensity now with the viewpoint of this point to set length scale, which doesn't care about what structural motif you're talking about, right? It's order agnostic, and ask locally if I put a cavity in this region or this region or this region, do I find effectively a bigger or smaller decorrelation associated with the point to set construction? And it looks like there's an anecdotal result in our paper which suggests that there is correlation with the structural or thermodynamic overlap and the regions of high and low propensity. And I think there's probably better data in this newer paper as well. So I think that's another interesting thing to go back to and really ask, you know, it's a time-consuming thing to do, but I think it's a very nice thing to sort of say, well, now I have a way to assess length scales associated with the static structure of the system. Can I look at that and the behavior of that in real space and actually map out the correlation with the propensity that I see in the dynamics? And the answer appears to be yes. So I'm running a little bit behind, which I apologize for. So I'll try to speed up a little bit and be even more superficial. So just to remind you what we've sort of covered, we've talked about dynamical heterogeneity in a qualitative sense. We've talked about length scales associated with dynamical heterogeneity. We've talked about the connection between static structure and dynamical heterogeneity, and then length scales associated with the static structure. Right, that's sort of what we've covered. What I want to go into a little bit more depth right now is how dynamical mobility propagates through the system. And one thing that I'll point out is that empirically, at least in some systems, it appears that there are longer length scale spatial correlations where motion of particles of the kind that I showed you form clusters, and those clusters basically cause motion nearby so that you have spatially correlated avalanches in the system. So that particle motion triggers particle motion in close proximity, and then that triggers motion nearby again, and so you have some spatial avalanche over some length scale that forms in the system. And as I'll mention in a second, there are theoretical models and pictures where this kind of propagation of mobility is natural. It's built into the model. The models are based on this kind of dynamical facilitation that also Jorge briefly mentioned in the morning. Okay, so just to show you how this might occur, and I'll be quicker than I might want to be. One can actually, various different ways one can calculate metrics for how a particle, relaxes. So if I look at the single particle level, I can have ways of asking whether or not a particle has escaped the cage of its surroundings. And there are different ways to do this. And what you find, though, in pretty much all of them is that the cage jumps, so to speak, aggregate spatially into clusters, and those clusters then aggregate into these kinds of avalanches. So basically you get cage jumps of local motion and that form some sort of correlated cluster, and then a correlated cluster of cage jumps will occur nearby, and that may propagate over some length and time scale in the system. So that, in a sense, we would call sort of a dynamical facilitation. And in fact, if you ask how that occurs in terms of the soft modes on a very short time scale, if I calculate the initial configuration and the propensity associated with it, then I get a cluster of cage jumps, let's say in one color here, which begets a cluster of cage jumps nearby, and so on. And over a time scale, let's say a third to a fifth of the natural relaxation time of the entire dynamical overlap, these things sort of live on top of the soft regions of the system. But then eventually, of course, the soft region of the system at time 0 doesn't mean anything for the system at time t. So the way in which these propensity maps themselves rearrange and how that relates to the elasticity of the system and the propagation of the mobility is I think, an unanswered question. But it is quite interesting that the dynamical heterogeneity that we've talked about basically forms this kind of spatial temporal pattern of avalanche-like motion. And I think this is something that I want to come back to at the end of the talk, which I think really deserves a lot more attention. Actually, let me skip this for a second and talk about supercooled liquid still, and then I'll go back to jamming systems. So as I mentioned before, this kind of facilitation, this propagation of motion where particle motion locally begets particle motion nearby and that propagates throughout the system is actually built in naturally to a class of models that are called kinetically constrained or facilitation-like models. And that kind of avalanche behavior basically is unbroken in these models. So the simplest kinds of models of this class would be something like I take a chain of spins. And I can have spins up or down. And let's say I look at a given spin. I want to know whether this spin can flip over. Okay, I look to the spin, let's say in this case to the left or right. You can define it either way you want, but let's say it's directional because that's going to give rise to the kinds of behaviors that we've talked about before in terms of other glassy properties. And let's say that spin is pointing up, then this spin can relax. Okay? But if I'm asking for this guy, the spin to the left is pointing down, he can't relax. Okay? The equilibrium distribution of up and down spins in the model is just set by, the Hamiltonian is trivial and the spins are uncoupled. So basically just the number of up or down spins is just set by the temperature, and it's not encoded in the Hamiltonian of the system, but actually just having that dynamical rule that I told you, where a spin to one side is up or down, allows the motion of the spin to the right, basically will give rise to many of the features that we've talked about throughout this tutorial. And in particular, you'll see cascades of motion that occur from the spins that are the ones that we would deem defects, the ones that are either up or down in whatever language that you want to set as the ones that facilitate the motion. So these are facilitated models. Clearly, these models are really, really antithetical. They're very distinct from the kinds of picture, or at least at first sight, the kinds of picture that Jorge mentioned. Actually, there are interesting connections between these, but at the very face of it, on low-dimensional lattices, the thermodynamics of these models are totally trivial. Okay? It actually doesn't mean that there isn't something closer to the kinds of things that Jorge mentioned. So I can find versions of models with Hamiltonians that when I talk about the local Monte Carlo dynamics of those model Hamiltonians, they give rise to these kinds of models. And from those model Hamiltonians, I could ask questions like, is there a growing point to set length scale in the system? So even though the thermodynamics are trivial, there are dual models that are thermodynamic that actually have growing point to set length scales and other features that allow us to maybe use computer simulation and experiment to distinguish different features. So some of the features of these and different predictions of different theoretical models. So some of the predictions of these models or the kinds of behavior that they yield, they can yield very realistic glassy behavior where you have non-exponential relaxation, you have non-Arrhenius relaxation in the transport coefficients. They are dynamically heterogeneous in the way that we've talked about. They exhibit Stokes-Einstein violation if you define properly what you mean by diffusion and what you mean by viscosity. They have growing chi4, and they do have growing, in these dual models, you can even define the point to set length scale, and the point to set length scale and the chi4 length will grow in these kinds of models. And the reason I bring these models up and skipped a few slides to get to this is that these models are very, very good models for, in some sense, capturing the kinds of things you don't have in the mean field models. So the particle hopping or the activated processes, which Jorge alluded to, that are hard to get in the infinite dimensional kinds of solutions that you have, are just, they're naturally put in by hand in these models. And so that's why things like Stokes-Einstein violation come out naturally in these kinds of pictures, which is very nice. It's actually not so trivial to get Stokes-Einstein violation in a realistic way from the d equals infinity solution, as far as I know. So the models also exhibit exactly the kind of behavior that I talked about here. That is, they have this kind of facilitated behavior. In fact, actually, the facilitation occurs forever, right? The avalanche occurs forever. Now, this is not really realistic. You expect that there's always the probability that this chain of motion is going to end somewhere because you could thermally activate something somewhere else. And so you wouldn't get perfect propagation of this kind of avalanche motion. And so this is something that I want to talk about now. How good are these models, and what are some issues with them? I think these models are useful starting points and inspiration for thinking about connections and differences with the mean field picture. So obviously one issue associated with these models is that the defects themselves are not specified. We might think about the defects as the soft spots in our configurations that we define through the propensity. Maybe they're associated with some local structural metric, and they're the regions that are most likely to move first. As I showed you before in this avalanche picture, the avalanches propagate on top of the regions of high propensity. at least in that one system that I showed you. So the defects themselves might be regions, defined as regions of high propensity, but it's not clear in the case of the model itself what that metric is, what that structural motif is. Maybe they're related to soft modes or something else, and these connections are remote. And so this is a little bit unsatisfying. In the models, and I won't go into this now, the models that are most closely connected with the phenomenology that we've been talking about in the phenomenology of glasses, the point to set length scale and the chi-4 length scale actually are the same. So, and Ludovic is looking funny, but I'll explain what I mean. If you think about, so if I take a model like this model, which is called the East model, this is the preferred model of people that advocate for facilitation being fundamentally important in these systems. The system that, or the Hamiltonian that's dual to this dynamical model is called the triangular plaquette model. And in the triangular plaquette model, the only length scale is the distance between defects, essentially. And so both the point to set length scale and the chi-4 length scale are just trivially related to 1 over the concentration of defects. There's no other length scale. This is not true in the square plaquette model, where there is a distinction, but that model does not properly map onto fragile liquids. So this is why I say that. And this we already know is not correct. Right? We know that, that in any system that has been simulated, the point to set length scale grows in a distinct way from the chi-4 length scale. So to me, this is an issue. This, in some sense, is a bigger issue for me, but I think it's actually quite an interesting one. If you try to atomistically map your system onto one of these models, as I said, you might sort of correlate the regions of high propensity with the defects in the system. And as you lower the temperature, the defect concentration will go down and down and down in a way that does seemingly correlate with a random distribution of these regions, which are just set by simple thermodynamics. And then the length scale that is the only important length scale in the system has to be the distance between these defects. And if you try to take your Lennard-Jones liquid and ask what is the distance between defects at the dynamical transition temperature, or something that would extrapolate to the dynamical transition temperature, it's very large. So it's something like 20 particle distances. Okay? If that was the fundamental length scale in the system, then you would expect large finite size effects in your computer simulations. Right? If you simulated 200 particles, you would expect the answer to be different than if you simulated 1,000 particles. But there's no difference. Actually, finite size effects in simulations of most models of supercooled liquids are extremely small. So it argues, at least in my mind, that the length scale that's important is not fundamentally the distance between the defects. I think this is very important. There's 2 other things that I think are interesting from the standpoint of the Simons collaboration, and also in part with what Jorge talked about in terms of the d equals infinity solution, which is that within the context of these models, the same fluctuations that give rise to the violation of the Stokes-Einstein relation that we started this discussion with is the same set of fluctuations that give rise to the growth of chi-4. So these things, because there's only one length scale in the model, these 2 things are really the same thing. Okay? But there's, I think, good evidence, maybe not perfect, but reasonable evidence that the temperature at which Stokes-Einstein starts to show sizable violations is distinct from the temperature where chi-4 starts to grow. So even in 3 dimensions, if I take a Lennard-Jones liquid and I ask where does chi-4 start to grow, it starts to grow right when supercooling really starts, where things are non-exponential or non-radius. But you have to go to a notably different temperature to start seeing the Stokes-Einstein violation to occur. Okay? Why is this interesting? I think this is interesting because of what Jorge mentioned in terms of simulations in higher dimensions earlier in the morning. So let's say I do what Patrick is very good at doing and has done very nicely, which is I take a system of hard spheres and I simulate that in 4 dimensions, in 5 dimensions, in 6 dimensions, in 8 dimensions, in 10 dimensions. I don't know about 12 dimensions, but what you see is actually very interesting. So and this is very nice work that Patrick did with Giorgio and with Francesco. If you look at the Stokes-Einstein value, so if you plot on your computer simulation your you know, your dynamical correlation function that you care about, it shows, you know, the behavior that we associate with standard three-dimensional systems, that timescales, this is log time, and this is the, let's say, the intermediate scattering function, which is the density-density correlation function. You see this multi-time step sort of, or multi-time scale kind of behavior with the plateau and some stretched exponential relaxation, and a relaxation time that's getting much, much larger as you cool the system down. But what you find is the higher dimension that you go to, the further away you can push away the hopping-like motion that we started this discussion with. And together with that, Stokes-Einstein violation basically goes away. Okay, so what you can do is you can open up a window, which is not surprising, where the infinite dimension system lives for a longer time scale. Right? If you then go to even longer time scale, let's say in 5 dimensions, you eventually get to a relaxation time where you see hopping and you see violation of Stokes-Einstein. But then if I go to a higher dimension, I have to go to a longer time scale to see that. You open a bigger and bigger window where the behavior of the mean field type dynamics that you expect in infinite dimensions lives. Okay? But the chi-4 is growing always at the onset of supercooling. So you can separate these two things more and more and more. So what this sort of suggests is that even in 3 dimensions, there is a distinction between the fluctuations that give rise to Stokes-Einstein violation and the fluctuations that give rise to the growth of chi-4, and that maybe some aspect of the dynamical heterogeneity, you know, we shouldn't necessarily only focus on the hopping-like motion. So the hopping-like motion is the motion that we would associate most with Stokes-Einstein violation, but maybe we're not focusing on the things that aren't moving, right, which is the viscosity, and that's the important thing here. And I think that that's really interesting. It's also true that there are 3-dimensional models where you can kind of see this. So one model is a very nice model of Mari and Kirchhoff, which basically you can take, let's say, pairwise interactions of particles, but on top of Ri minus Rj, you can give a random shift to the particles that's basically over any distance scale. You have a distribution of these random shifts. If you take the width of this distribution as 0, you get back your regular hard sphere system or what have you. But if you take that width to get very, very large, you have more and more of a mean field-like system. And you can tune this by hand naturally from this distribution. Or maybe less abstractly, you can take a model like the Gaussian core model, which is a realistic, in a sense, interaction potential where particles interact instead of by a Lennard-Jones potential, they interact with a Gaussian potential. So it's finite at r equals 0, so the particles can squish through each other. And if you go to very high density in that system, you basically have a mean field-like scenario because the distinction between the hard core that you have in your normal potential and the long-range part is minimal compared to what you have, let's say, in the Lennard-Jones system. So basically, over some long length scale, particles are interacting the same way, or more or less the same way. And what you find in that kind of system is that like mean field theory predicts, the dynamical susceptibility grows enormously large, but the things like Stokes-Einstein violation are suppressed. In fact, they don't exist at all until you get to a very low temperature. So those kinds of systems are 3-dimensional systems that really very closely follow the mean field scenario. And it's interesting to ask, what does the dynamical heterogeneity look like in those 3-dimensional systems? And it looks quite different. All of this sort of very eye-catching hopping-like motion is suppressed, and you see very, very long length scale, large fluctuations from sample to sample. And so the question that I have that I think is unanswered but interesting is, how much of what we see in 3 dimension is really this background kind of behavior that's making, let's say, chi-4 grow or not, or how much of it is not? I think this is a very interesting question. Either way, I think it basically goes back to the fact that even in 3 dimensions, it looks like the fluctuations associated with, just one second, with Stokes-Einstein violation and those of chi-4 are different fluctuations. They occur, their onsets occur at different temperatures. And this is what you would expect as you go, that's more and more the case as you go to higher and higher dimension. Sylvia?
Yes, what happens to the ISO configuration of susceptibility?
Yeah, I don't know. I don't think it's been looked at. Okay, the other question is what happens in the kind of avalanche-like motion that we started this discussion with. In the facilitated picture, you would expect that the avalanches are perfectly conserved. So a natural question is, as you go to lower and lower temperature in the real system, is the avalanche motion more prominent or less prominent? There's some evidence, which may be not the best evidence, but there is some evidence that as you go to effectively higher densities or lower temperatures, actually what you have is distinct from what you would expect in the kinetically constrained picture. Yes?
Can I make a small criticism of the word avalanche?
Yes.
Because avalanche is usually considered to be something irreversible.
Mhm.
Falls on you and that's it. But these things are time reversible. So they are correlated, but they're not.
I mean, I assume that I can do this in the Brownian system as well, right?
Yeah, but statistically, because of detail balance, these situations and the time reverse would be equally probable.
Okay, fair enough. Right. I use the term loosely just to basically say that the dynamics are facilitated,
Yeah.
that there are clusters of rearrangements that beget clusters of rearrangements nearby, and that propagates through the system in a spatially correlated and local way.
But the reverse process is equally probable.
Sure.
Is it so? Because you dissipate, this whatever, the facilitated motion dissipates energy as it goes along. You have to collect all of that entropy back, right?
But if the detail balance and the energy at the beginning and at the end are the same, then and you're in equilibrium, so I mean, there's nothing you can do about it.
Okay. I don't disagree. So all I want to say about this is I think there's some evidence that what you would expect from facilitation pictures as you go to lower temperature might not be true. But I think a lot more work needs to be done, which I'll come back to in 10 minutes or 5 minutes when I'm done, in a list of things to do. So I think basically what I'd like to sort of say about this is that facilitated models actually seem to be very, very good models of the hopping motion, that is the motion that gives rise to Stokes-Einstein violation. Whether or not it is complete in giving a picture for non-mean field-like behavior in 3 dimensions, I think there are a lot of reasons to think it is not. And I think this is something interesting to follow up on. So what I briefly skirted over, and I'll still be brief because I wanted to get to it when we were talking about avalanche motion, is one can see some aspects of the same things in systems near the jamming threshold. So this is nice work that Mathieu had done 5 or 6 years ago. Basically, if you look at small systems that are close to jamming, you can see sort of large scale, the equivalent of what I would call cage jumps before. And if you project that motion onto the soft modes, the soft modes very faithfully form a basis for that kind of motion. And as I get closer and closer to the jamming threshold, the number of soft modes, the fraction of modes that I need to reproduce the kind of motion that I see in the system is smaller and smaller. There's some degree of correlation that you can see in the same way in thermal systems, but it's much less dramatic. So I think this is a very, the systems near the jamming threshold are very interesting to think of from this standpoint. And this is what I mentioned before. Just in some sense, the connection between soft modes and dynamic heterogeneity in jamming systems and thermal supercooled liquids is an interesting connection to pursue. In some ways, there has to be a difference. So this is work of Sid's, but if I go back and do the same thing that I showed you earlier and take the soft modes of the system and look at the real space polarization of those soft modes as they get closer and closer to the jamming threshold, because there's marginal stability at jamming, I expect that there should be an actual diverging length scale associated with the modes. And there's evidence that that is true. So I think there are nice connections between what I've told you in terms of dynamic heterogeneity between coming down the line that Jorge drew on his plot from the y-axis to the j point. But there are also definitely differences that are worthy of thinking about. Okay. I think there's probably not that much patience to go through this. I have basically 2 more slides, but they're sort of disconnected from everything else. Let me just, I don't know. Let me just mention this. So another interesting thing that I think is definitely worthwhile of study within the context of this collaboration is thinking about something that at first sight is very different from dynamical heterogeneity, which is the behavior of frozen solids made out of glasses at very, very low temperature. So it's been known, I think in 1971 or 72, Zeller and Pohl's papers. 71. So in 1971, Zeller and Pohl measured thermal properties of glasses in the range of 1 Kelvin. And unlike what you would expect from what you learn in your undergraduate solid state class, that you have the Debye model, and on some length scale, even though the system is disordered, your glass looks like some chunk of dielectric material. It shouldn't matter that it's disordered or ordered. You should find that you get long wavelength like phonons in the system, and the specific heat should grow like T cubed. But what they found is that the specific heat grew like T. Okay, and if you measure the thermal conductivity in the system, it should grow like, I think, T cubed. But they found that it grew like T squared. Okay, so, and about a year later or so, a model was put forward which sort of has been accepted, but it's very not microscopic in a sense, and maybe is lacking in some ways, which is called the two-level system model. And this was put forward by Anderson, Halperin, and Varma. And basically what they postulated was that at very low temperature, the system has a small number of active tunneling systems where there are configurations where the system can tunnel between two sites. Of course, in their paper, they didn't say what's tunneling. Is it 30 particles moving or 2 particles? But basically, they took some pretty weak assumptions that if you have a two-level system, your Hamiltonian for your two-level system is a tunneling matrix element. Right? There's a bias energy, which is basically epsilon, and then a tunneling matrix element, delta, that can connect these two states. There won't be many two-level systems that are active at 1 Kelvin because you need the tunnel splitting, which is square root of epsilon squared plus delta squared, to be on the order of 1K. Otherwise, the two-level system is frozen. Okay, so something like 1 in 10,000 per atom two-level systems will give rise to a behavior that if you had a distribution of these two-level systems, and basically what they said was the epsilon and the delta will not be correlated. The probability distribution of epsilon they'll take as flat, because it doesn't matter whether or not you have plus epsilon or minus epsilon. That just reverses this. And you're at very low temperature, you can basically take whatever distribution you want. And if it's even in that variable, you can take it to be flat around small energy. For the probability of the tunneling, they said the probability of the tunneling matrix element delta goes like 1 over delta. And this is easy to get from the WKB model of tunneling. If you say that the tunneling matrix element goes like e to the lambda, where lambda is some barrier property, and you change variables from lambda to delta, and you say that the lambda variable is flat, then you'll get a probability distribution in delta that goes like 1 over delta. So if you just take these assumptions, probability in epsilon is flat, probability in delta is 1 over delta, here are your Hamiltonians, and you have a random distribution of them, you'll get that the specific heat goes like T, the thermal conductivity goes like T squared, and so on. So you can ask, how true is that? And I think that's a good question to ask. There is a lot of evidence that's been accrued in the last 50, 40 years that supports this picture. So maybe the most direct evidence is you can put a optical impurity in your glass at very low temperature. That optical impurity will couple to the phonons that are emitted by a flipping two-level system. So I take a two-level system and it tunnels, it's going to spit out a phonon, and that phonon is going to make the optical transition that you can measure change. Right? Every time you absorb a phonon, it's going to go like this. And every time you absorb another phonon, it's going to go like this. And if you look at the traces of the optical transition, they look like they flip between just two states. Once in a while, you can see 3 states. So there's some corrections to this, but it's reasonable. There are other things that are predicted. So if you do a hole burning experiment, where you do a nonlinear experiment where you take the inhomogeneous ensemble of the system, you bleach it, you get a hole in the system, you look at the time evolution of the hole from spectral diffusion of the flipping of the two-level systems, it's predicted in the model to be logarithmic in time, and that's also measured. So these are some evidence for this, but one thing that's definitely left out of this model is what are the two-level systems, what's moving. There are also very interesting connections with the glass transition. So it's been known for a very long time that in some sense there seem to be correlations between what you would expect for the amount, let's say, of dynamical heterogeneity that's frozen in at the glass transition and the density of two-level systems. So one speculation you could make is that the two-level systems are the remnants of the dynamical heterogeneity that we talked about. And they're just the little pieces that are left of these clusters that can't move through the system anymore. They can just move back and forth locally. That's entirely plausible. I'll show you a picture in a second that makes this connection ever so slightly more tangible. The other question is, as you raise the temperature, of course, things are not going to be two-level systems anymore. There's got to be some connection to anharmonic modes of the system, and how do you marry these pictures together? So I think one of the things that would also be nice is to try to gain a deeper understanding that synthesizes what we can learn in this collaboration from our understanding of dynamic heterogeneity, and also from our understanding of quantum mechanics and our understanding of glasses at low temperature, and sort of really make an overall synthesis of this. This is just one thing I wanted to say that's very funny to me, which is Andreas Hoyer, when he was a postdoc, did a lot of work trying to understand what was really happening in real space in these two-level systems. And they found that a lot of them are collective, sort of like what you would think of when we do the simulations of dynamic heterogeneity. And they also noticed that the motion was often string-like, and they called it snake-like. And this was, a good 10 years before Sharon Glasser got famous for talking about strings and dynamic heterogeneity. It's interesting, and I think this is an underused, understudied area that would be really nice to think about. Okay, so let me just finish up by, I wrote down a list of questions that we don't have to discuss because everyone's tired and we're already exactly at 2 hours, but I only have 2 more slides. They're all just bullet points of things that would be really nice goals from my perspective to think about that are connected to this real space set of questions. So one of them is, Jorge talked in the morning about a D equals infinity solution. This is one of the amazing achievements that made this collaboration possible, that in the last few years, people in this room have really understood jamming very, very nicely to the quantitative level of predicting exponents that seem to be valid in low space dimension, have solved the D equals infinity dynamics for the first time and shown that it's not precisely exactly mode coupling theory. I think the deepest and hardest question in the realm of sort of three-dimensional dynamics of supercooled liquids is how do we take that solution and marry it with what we know that's very much non-mean field in 3D? How do we, for example, put activated processes in? How do we understand hopping motion? Can this be done from a perspective that builds on the D equals infinity solution, or should we just put it aside and start from scratch, which I would hope the answer is no. In particular, because I tried hard, and I think honestly, to say there are indications of behaviors even in 3 dimensions that look very mean field-like. So the hope would be that one could, but I think this is one of the hardest things to do, and this is, I think, would be a big, big achievement in understanding the dynamics in 3 dimensions by building on this framework to understand things that seem to be associated with non-mean field effects like hopping motion, the avalanche kind of behavior, and so on. So in the point of perspective of avalanche behavior, there are lots of questions to ask, and some of them I think are begged immediately when you look at the very few papers that have been done. Is facilitation more or less conserved? How does this depend on spatial dimension? How does it depend on the system? One of the nice things that's been brought up in the questions is that there are much better ways to do equilibrating of systems. So the kind of thing that Ludovic and Giorgio mentioned, particle swapping. If you find the right system where you don't phase separate, but you are able to equilibrate the system to lower temperatures, I think you can answer lots of questions that need to be answered. And again, from the standpoint of avalanches, can we understand this from the mean field perspective as well, connecting to work that, let's say, Giulio has done with Gilles Tarjus and other people? I think this would be extremely important to do. One thing I didn't talk about at all is the Gardner transition, but in low space dimensions, what are the real space or the implications in general for this? I think this is an unanswered, very interesting question. I really skimmed over jamming, but I mean, obviously, as I said, there are connections from the soft mode perspective and other perspectives. In particular, from the avalanche perspective, connections between jamming that we see as we work at 0 temperature and change the density of the system slowly. And I tried to allude very briefly at the end, are there connections between dynamic heterogeneity and defects in glasses, both at the level of the supercooled liquid, which is what we spent a lot of time on, but also at the level of what we call two-level systems in glasses. And I'm really tired, so that's where I'm going to end. And if you want to ask questions, please do. Yes?
So I apologize, I missed the first part of your talk, so if I ask something that's redundant, just shut me up right away. But you sort of made a careful distinction between sort of the Stokes-Einstein violating hopping things and maybe more bulk, high floor like things and how they happen on different temperature scales. And so one question I have is sort of, what do you think are the relationships between the structures that sort of facilitate those different things? Or do you think that's known, or like, what do you think?
I don't know. Maybe Patrick looks like he has an answer for you.
I mean, is this something we know, or is this something we need to think?
I think, in my mind, it's something that's not completely understood, but
It's something we need to think about. In the limit of infinite dimension, we probably have a good idea how to do it, but it's not been done, it's not solved. In finite dimensions, especially once it becomes facilitated, all bets are off. But that's for the hopping and facilitation part. The other components should not have a structural signature, right? In a sense, if you want to be doing if you want to be separating the two, you need to find a way to subtract the background of one from the other. Right? Figure out what is the structural part, what's left over.
I think also there may well be a mean field way of looking at things like avalanches. And you wouldn't talk about things like spatial correlation in the sense, but you could ask the question, maybe Giulio could say more about this, but I think there are ways to address in mean field systems what the analog of an avalanche would be, even if it's not spatially correlated in this sense. So this is actually one of the things we want to do in this collaboration.
I was wondering related to this question, is anyone doing any work with the lattice class models like you and Giulio previously were working on? I mean, is there any work in using that kind of model to study these things?
Yeah. Yeah, I mean, so a lattice class model is a model that at first sight seems very much like a facilitated model, but instead of basing the motion on a dynamical rule, you base the allowed motion on a configurational rule. So basically what you say, for example, is take a square lattice and you're only allowed to put particles on the lattice that have no more than a certain number of neighbors around them, okay? And so basically as you change the density, there are going to be fewer and fewer configurations that are allowed. And then you just make local moves, and if you have no local move that is allowed to connect the configuration, you're stuck. If you can move locally to a configuration where that configuration is allowed thermodynamically, you're not stuck. One of the first things you immediately realize is, and I think Giulio doesn't agree with this, but it seems obvious to me, is that this is why it must be wrong from my perspective. It seems that it has to be true that the motion is completely facilitated as well. right? Because the motion is just local. You move a particle. If you move, you move. If you don't, you're making local Monte Carlo moves. So I would assume that these models, even though they're not based on facilitated rules, are also completely facilitated. So one of the lessons you learn from that kind of perspective is just because something is facilitated doesn't mean that the facilitated perspective is the right one. I mean, these are models that are configurationally based. They're models that in infinite dimension are random first order. So I think that's interesting. I mean, one of the things that I didn't discuss, but I showed this plot from Ludovic and Rob's paper of the predictability from the propensity, that if you look collectively, you can predict motion over some longer length scales, but if you look on the single particle length scale, the predictability always stays very low. In certain lattice glass models, that's exactly what you find. That if you look at the particle level, there's a big decoupling between collective and single particle-like predictability. This seems not to be true in the lattice versions of things like the Cobb-Anderson model. So I think that's also interesting. But overall, the answer to your question is, I don't think a lot has been done that's systematic that addresses the questions that I think are relevant for the collaboration.
So I guess I just want to make one comment because it's my job. That we've heard a lot of theoretical aspects of this and some new things and Gardner transition, all this stuff is very exciting, very new. But what I guess I would still like to see this collaboration push towards is, okay, so what are the experimental consequences of these things? That is, I'm not sure, having heard a lot of this today, I'm still struggling with the activity. So how do I go and see this in real systems? And I mean, I think that's an open question.
I mean, one of the things that you might not agree with, but I feel is in the similar spirit, is over the last 15 years that I've paid attention to this field, even if I haven't worked on it entirely over the last 15 years, is trying to use anything, whether it be experiment or even good computer simulation as sort of in silico experiment, to distinguish between different theoretical perspectives so that we can move forward. And one of the frustrating things is that it's surprisingly hard to differentiate seemingly very, very different pictures. So I would even be happy if we could do much better simulations that could go to much lower temperatures, without any influence from finite size effects or anything else, that we could use as very, very sharp ways to distinguish between theoretical pictures. I would view that as not as good because everyone likes a definitive experiment, but to me those are also experiments. So I totally agree with you, but I feel that that in part, hopefully our advances in being able to do better simulations will allow us some measure of doing this as well. And I feel like it's not that people haven't tried. It's just one of these frustrating things that someone who has a perspective that's very different than yours always has a good way to explain the same thing you think you definitively explained with your favorite theory.
It's still just the issue of, even if finding what experiments will tell you what is the right explanation of theory. I mean, that's great, and that's certainly one of the jobs done, but another job is actually say something that will qualitatively open up something new in the experiment.
I agree.
That would just be really
Right.
very
Sometimes those things are born right out of the theory. So, one of the things I mentioned, which I glossed over, was this ensemble dependence of chi-4, and that has led to a very facile way of experimentally estimating what these length scales are. And then that's very nice, and you can do that in real experiments, but then you find length scales that are both very satisfying on one hand and seem to very much disagree with what you see in the computer, which brings up more questions.
So I would like to say two things. One is all the intermediate relaxations are, to my mind, essentially absent of all the theories we discussed. So these are experimental facts that we don't observe. That we don't, for the moment, have an explanation. So that's a place where, as I was asking you before, do glasses made of spherical particles have intermediate relaxations? It's anybody's guess, but certainly the infinity will not see them. that's an experiment. And related to this, it has to be liquids, because, I mean, let's face it, colloidal stuff is now in the domain of numerical times and sizes, so irrespective, I mean, you're going to publish it in a better journal, as Silvio was saying a while ago, but essentially you're getting the same information. This has to be faced, and it's true of spin glasses to a large extent now. So I think that this, between people who just see easy. But this will happen more and more. I mean, liquids are still, I believe, beyond anything. But this, if you only want the truth and you're not only, I mean, well, you're not. So that's something to take into account.
I have a comment also on Sid's comment. So there's a very large community of people doing scattering experiments on glasses, and Mathieu and I tried to reach out to them a few years ago to show that they're thinking about the boson peak and everything in terms of disorder as affecting boson peak, but we were trying to argue that the genetic point of view and soft mold all this can explain the dynamic structure factor and all the stuff that they're measuring. So I think there's a lot to be done there, especially putting in context the Gardner transition into regular Gardner phase and that the margin stable phase. What does that mean for boson peak and dynamic structure factor? All the stuff, sound attenuation that we're measuring have really good results for.
It's not probably related to your talk, but it's another aspect of systematics. I think a promising direction to go to make contact with experiments is the one of elasticity and the origin, what happens when you take a solid material. Because there, I mean, there is the work of Julian and Francisco, shows that in the Gardner phase you have a lot of anomalous behavior going to the elastic measurements. And also if you could study, for example, what happens when you have avalanches and things like that, maybe we can make solutions. And I don't know, I don't know how it matches with the real space, but I think also with this idea of defects, you can...
Oh, I totally agree. It was you who asked me to talk about real space, so I wanted to confine everything that I said to real space.
But I think this is the direction to go both in the
I agree.
field and the real space approaches. I think also in real space you can study what happens when you share the system and you have defects and avalanches. And there I think experiments are more easy.